will just take you through some of the people who have been involved in this. So the development of quantum mechanics was Max Born, Heisenberg, Pauli, and so on and so forth. And there, Born actually used this word quantum for the first time in 1924 or so. So next slide. I'm not taking you through in these slides. I'm taking you through the main people who were involved in the development of this thing. So one of them is Max Planck. As I told you that when we wanted to explain this thing, he assumed that all this energy has to be in some quantum or a unit is not continuous. So this is the basic point, and we'll come later on to actually what is this quantum about. But what it meant was these things are not continuous but in discrete, and Max Planck got the Nobel Prize in 1918 for his contributions. But as I said, he himself initially did not believe. So he said, this gives me the answer, but what is happening? And it was not only Einstein came up with his thing, and then all these people together kind of said that, yes, this is a common set of beliefs that we can have. Next slide. Next slide is about Niels Bohr, and I told you he was the one who kind of said that the atomic structure, and that can be explained by this thing, and he got a Nobel Prize in 1922. So you see it's around the same time that things are happening. Next slide. Albert Einstein got a Nobel Prize in 1921 for the photoelectric effect. So they all came from different directions, but converged towards a common set of beliefs, which is called the quantum theory. Next. Now, de Broglie's contributions are also very interesting. He also got the Nobel Prize. And so let me now come to something, in a sense, flashback. So you all know in your optics things that in geometrical optics, we believe that light travels in a straight line. And when light travels in a straight line, it's called rectilinear optics or whatever. People like Newton, they believe that it is a series of particles which is just flowing, and that's why you have properties of reflection of light, angle of incidence is equal to angle of reflection. You also have refraction, where there is determined by the refractive index. On Newton's himself observed a thing called Newton's rings, which is a series of fringes which come when there is a thin film of air, and is something which you see when water spills over oil. You see those things also, the fringes, etc. And this is a kind of interference of light. So people like Huygens, etc., talked about wave optics and wave theory. And so in light, we realize that light can be corpuscular as well as a waveform. And both these things are kind of dealt with at the school level. Schrödinger, so let me continue with this thing. So the point was that this was there, but we still believe that electrons were something different. And in fact, Father Thomson got a Nobel Prize for showing that electron is a particle. And his son Thomson got a Nobel Prize for showing that the electron is a wave. And de Broglie got a Nobel Prize for saying it is neither particle nor wave. So now this is what was becoming interesting. So we realized, but not quite understood, that light has both particle behavior and wave behavior. And electron also has particle and wave behavior. And what de Broglie said, that everything has a particle and wave behavior. And he created a de Broglie equation which told the wavelength of the quote-unquote particle with a certain momentum and velocity. This is the fundamental concept of quantum mechanics, and we will come further. So one of the key concepts of quantum mechanics is that particles and waves are not necessarily two distinct things, but all pieces of matter at some point of time show wave-particle behavior duality, which is we might call a quantum behavior. Schrödinger talked about, so what happens? How do we describe it? In classical mechanics, we use Newtonian formula to describe things and where the particle will be, etc. So Schrödinger talked about a wave equation for this, and he also got a Nobel Prize in 1933. Next slide, please. Heisenberg is well known because once you start saying that it can be a wave or a particle, both, so we basically came to the idea that so you will never know where a thing is. See, in classical mechanics, we say if a thing is starting with this velocity, going at this speed, at this point, it will be at this place. And you could calculate everything from v is equal to u plus ft, s is equal to half gt square. But Heisenberg said when you get to very small, you will not know both the position and the momentum at the same time. And this is called the Heisenberg uncertainty principle. And he also got a Nobel Prize in 1932 for this. Next slide, please. Dirac is again another brilliant. He did not look at the wave part, etc. He had a different mathematical way of doing it. But Dirac's contribution was that he also got a Nobel Prize. So his contribution was that he tried to look at Einstein's theory of relativity and Schrodinger equation of quantum mechanics, combined the two and created a new equation which was called the Dirac equation. But the beauty of Dirac's work was that when Dirac did this thing, he found there is going to be symmetry between the various things. And therefore, he concluded that if there is something called the electron, there must be a particle which is the opposite of it, which is called the positron. See, just like, let me go back to something simple. When you are asked, let us say, if x squared is equal to 4, what is x? So you will simply say 2. But if you're more careful, you say it can be plus 2 as well as minus 2. That is the thinking which Dirac put. Now, if there is a particle with a certain mass and a negative electric charge, then just like we said, plus 2 and minus 2 are both solutions of x squared is equal to 4. The solution to Dirac's equation would imply that there is another particle with the same mass, but a positive charge. And he called it the positron. Now, it is interesting. This was said purely theoretically. The positron was actually discovered several years later, for which again somebody got a Nobel Prize. But the point is, and I just want to tell you that today it is a basic diagnostic tool in cancer research. If you know of somebody who unfortunately had cancer, etc., and testing is going on, one of the methods of testing is called PET, positron emission tomography. See, X-rays have been discovered much earlier, 1900 or so by Röntgen, and X-rays were used for diagnosis, but this positron emission technology is being used for diagnosis. And what I want to share with you is that the future is about many more quantum technologies being used for medical diagnosis. The whole thing of quantum sensors is going to be something which is going to be very important. So Dirac did this. Now, next slide. So next slide, Richard Feynman is a different generation. So all these people did their work in 1920s, 30s, etc., etc. Richard Feynman, by the time he grew up, all this had been done. So Richard Feynman is credited with creating the further thing. Firstly, he created a method of interpreting quantum mechanics, which is very different. So whereas Schrodinger's equation model is the probabilistic wave equation, Dirac, etc., talked about matrices and certain kind of vector spaces, Feynman had a completely different approach. He had what was called the path integral approach to quantum mechanics. So he says that when something moves from state A to state B, there are a number of possible paths. And the probability of each path is dependent upon something. And the other thing that which he is very famous for are what are called Feynman diagrams. So traditionally, we use equations in physics to describe various things. He used a set of diagrams. So there would be straight lines for electrons and fermions, wavy lines for other things, and so on. And he developed this whole field of quantum electrodynamics and so on and so forth. So he was again awarded the Nobel Prize in 1965. But as I will tell you, 1981, he proposed the idea of a quantum code. This is a very famous picture, and I really like to share it. This was some Solvay conference where there's a large number of Nobel Prize. I think that people say that this is the picture which shows the highest amount of intellect in a single frame. These things are labeled. You can look up if you're curious. You can go to anything and Google for the Solvay conference photograph, and you will get to see. You can see Albert Einstein, you can see Madame Curie, you can see so many other people. But the point I wanted to make here is very important, that quantum mechanics is the effort of a large number of brilliant people each of which got a Nobel Prize separately. And that is why you are seeing its kind of, impact that will be happening, etc., etc. Unlike simple electricity, which Faraday did, or something else which somebody else did, or even the Darwinian theory of evolution, which Darwin did. So